Okay, everybody, welcome to the third day for the second week, and Alberto is going to continue with his lectures.
Okay, thank you very much. So we can continue with this mini course on closed G2 structures. And after the first two lectures where we saw some introductory part to G2 structures from a general point of view, we will, starting from today, we will focus on closed G2 structures. So let's start recalling something we saw 2 days ago, and which is the following. So when we have a G2 structure, which I shall continue denoting by phi, which is a non-degenerate reform defined on a 7-dimensional smooth manifold that I shall denote by M, then it is torsion-free meaning that the holonomy group of the induced metric is a subgroup of the group G2, if and only if these two conditions hold. We want the three-form phi to be both closed and co-closed. Where here again, let me recall that this star here denotes the Hodge dual operator induced by the metric induced by the three-form. So this point of view gives rise to, let's say, two different types of G2 structures that can be considered and studied on their own, which are those whose defining three form satisfies this condition here, which are the so-called closed G2 structures, and those whose defining three form is actually co-closed, and so are the so-called closed G2 structures. So we say that a G2 structure phi is closed if the defining three form is closed and it is co-closed if the four form given by its Hodge dual is closed. So these are two of the possible 16 classes of G2 structures arising from Fernandez-Gray classification. And of course, they are of particular interest because these two conditions together imply that the G2 structure is torsion-free. And so we have the reduction of the holonomy group. Let's see some comparison between these two conditions here. So first of all, as you can see, the equation asking phi to be closed is linear in phi, while the condition requiring phi to be co-closed is not. It is nonlinear in phi. And this is because, recall, this is because of the fact that the Hodge dual is induced by the metric which is induced by phi. And so this is similar to what we said 2 days ago regarding the condition nabla phi equal to 0, which was also nonlinear. So from this point of view, this equation looks better because it is linear, so it is much nicer if one has to deal with it. However, if you think at these equations locally, so you write down them with respect to some coordinate chart, so with respect to some local coordinates, then the equation d phi equals 0 is a condition on a 4 form. So this will give you, in general, 35 equations locally. While the condition requiring phi to be co-closed is a condition on a 5 form, and so this locally will give you 21 equations in the most general case. And so from this point of view, you can see that the first condition is actually much stronger with respect to the second one, as you need more equations to define that. Moreover, what it is possible to show using an H-principal argument is that both closed and co-closed G2 structures exist on any open 7-dimensional manifold admitting G2 structures. And this is because if you think, for instance, the similar result for symplectic structures, the idea here is that the 3-form phi and also the 4-form star phi are sections of some open subbundle of the bundle of 3 forms and 4 forms respectively. And when the manifold is open, you can argue, as in the case of symplectic structures, and as in the case of non-degenerate 2 forms on even dimensional manifolds and symplectic structures, to obtain an homotopy between the set of, let's say, G2 structures and closed and co-closed G2 structures on open 7 manifolds. And so in particular, you pick any G2 structure on the manifold, and you will find a closed G2 structure and a co-closed G2 structure that is C0 close to the 3-form you picked. In the compact case, this is true only for the co-closed G2 structures. And this is a theorem that was proved by Crowley and Nordstrom in 2015 that tells you that co-closed G2 structures exist on every compact 7 manifold admitting G2 structures. And we do not have any result of this type for closed G2 structures. So in general, nothing is known about the existence of closed G2 structures on compact manifolds. And on the other hand, as we saw in the last lecture, closed G2 structures play a prominent role in the theory of G2 structures, as the only known result we have ensuring the existence of torsion-free G2 structures on a compact manifold, that is the theorem by Joyce we stated in the last part of the last lecture, requires the existence of a closed G2 structure whose torsion is small in a suitable sense. So, on one hand, we do not have general results ensuring the existence of closed G2 structures on compact manifolds. But on the other hand, all known and potentially effective methods to obtain torsion-free G2 structures on compact manifolds require the existence of a closed one. And here, with potentially effective methods, I mean, for instance, the Laplacian flow for closed G2 structures that we will consider tomorrow. And so if you remember, for instance, all the constructions we have of compact manifolds admitting torsion-free G2 structures and actually having a microequivalent holonomy G2 are manifolds that are constructed in such a way that they admit at closed G2 structures satisfying the hypothesis of Joyce's theorem. So these observations here let us focusing on closed G2 structures. And let me recall that in such a case, we have that by definition, the tree form is closed. And then if you remember the discussion about the intrinsic torsion forms, the differential of the four forms star phi is equal to a certain two form tau 2 wedge phi, where this two form tau 2 belongs to the space of two forms that is pointwise modeled on the G2 irreducible 14-dimensional submodule of the space of two forms. So in particular, this means that by definition, tau 2 wedge star phi is equal to 0, and tau 2 wedge phi is equal to minus the Hodge dual of tau 2. And just observe that this first condition tells you that, of course, the remaining intrinsic torsion forms are all 0. So from now on, since we have only one of these intrinsic torsion forms that is involved in our discussion, I shall denote it simply by tau. Since there is no risk of confusion. So what do we know about closed G2 structures? As I told you in the first lecture, today we will focus on closed G2 structures from two points of view. From the point of view of curvature properties and from the point of view of symmetries of closed G2 structures. So let's start talking about curvature constraints. And this is based on works by Bryant and Clayton Ivanov, both around, let's say, 2005. So what, in particular, Bryant proved is that given a G2 structure, it is possible to describe both the Ricci tensor of the induced metric and the scalar curvature of that metric in terms of the intrinsic torsion forms. And if you have a look to its paper, you will find the explicit description of both these objects. In the case of closed G2 structures, what you have is that the scalar curvature of the metric induced by a closed G2 structure is given in terms of the intrinsic torsion form tau as -1/2 the square norm of tau. So in general, for a closed G2 structure, you have that the scalar curvature of the induced metric is non-positive, and it is equal to 0 if and only if the G2 structure phi is actually torsion-free. In fact, from here, from these defining conditions, you immediately see that a closed G2 structure is torsion-free if and only if it is co-closed, and this happens if and only if this intrinsic torsion form tau, or tau 2, is equal to 0, so if it vanishes. As for what concerns the Ricci tensor, you can write it in terms of the intrinsic torsion form tau as follows. It is given by 1/4 the square norm of tau times the metric G phi minus 1/4 that G2 invariant map going from the space of three forms to the space of symmetric tensors we defined in the first lecture, applied to the three form d tau minus 1/2 the Hodge dual of tau wedge tau. Now, from this identity here, if you apply the map I phi going from symmetric to tensors to three forms, whose point and the pointwise definition of this map was also given in the first lecture, then one gets that the exterior differential of tau as the following expression. It is 3/14, the square norm of tau times phi plus 1/2 the Hodge dual of the fourth form given by tau wedge tau minus 1/2 this map I applied to the traceless part of the Ricci tensor of the metric G phi. So in particular, from this identity here, you see that if phi is a closed G2 structure, then the metric it induces is Einstein, as the trace-free part of the Ricci tensor is 0, if and only if d tau has this expression here. Now, using this fact, together with the fact that tau belongs to the space omega 214, so which means that tau wedge phi is equal to tau wedge minus the Hodge dual of tau, as we recall earlier. And so this is minus the square norm of tau times the volume 4. And moreover, you can show that if you take the norm of tau wedge tau and you take the square of it, then you will obtain the norm of tau to the power of 4. And using these two properties here that can be shown pointwise, and you compute 1/3 of the exterior differential of the wedge product of tau with itself of 3 times, some computations give you that this is equal to 2/7 the norm of tau to the 4th times the volume form of the metric induced by the 3 form. So if you have a compact manifold and you integrate these two expressions, this expression over a compact manifold, then this object here will be 0 because of Stokes' theorem. So in this case, this implies that actually the norm of tau has to be 0, and so that tau has to be 0. So what you get, and this was proven independently by Bryant using this argument here, and by Clayton and Ivanov using a different argument, is that on M compact 7 manifolds, the metric induced by a closed G2 structure phi is Einstein. So its Ricci tensor is proportional to the metric itself, or equivalently, the traceless part of the Ricci tensor is 0, if and only if phi is actually torsion-free. And so in particular, Ricci flat. So this means that you have a restriction on the curvature if you want. And so in the compact case in particular, you cannot have closed G2 structures that are not co-closed and induce an Einstein metric. In the non-compact case, we know something in the homogeneous setting. And in particular, this was proved by Fernandez, Fino, and Manero. in 2015, what they proved is that if you consider a simply connected solvable Lie group of dimension 7 endowed with a left invariant closed G2 structure, then the induced metric also in that case can't be Einstein unless the G2 structure is torsion-free. So what they prove is that a 7-dimensional simply connected solvable Lie group cannot admit left invariant closed G2 structures inducing an Einstein metric, so such that G phi is Einstein, unless phi is torsion-free. So in particular, this means that G phi is actually flat. Since in this case, since the tree form is torsion-free and you have a left invariant Riemannian metric, you have that the Ricci tensor is 0, so it is Ricci flat. And then in the homogeneous setting, this implies flat by a result of Alexievsky and Kimmelfeld. Which was proven in 1975. And let me also remark here that to get to today, we know that Einstein solved manifolds, so simply connected solvable Lie groups with a left invariant Einstein metric, exhaust the class of non-compact homogeneous Einstein manifolds. This was conjectured by Alexievsky, and you can find the statement of the conjecture in the book by Besse on Einstein manifolds. This was proved for some dimensions, including dimension 7, by Arroyo and Lafuente in 2015. And then this year, this conjecture was proved in full generality by Böhm and Lafuente. And you can find the paper on the archive. So this class of Einstein, of homogeneous Einstein manifolds that are non-compact exhaust the class of non-compact homogeneous Einstein manifolds. And so this gives a complete answer in that setting. An open problem related to this fact, so related to this property of the metric of being Einstein, is the following. So we do not know whether there exists even incomplete closed G2 structures such that the induced metric is Einstein and non-Ricci flat. This is an open problem so far. And as last remark, let me also recall that Brian proved that on a compact manifold with a closed G2 structure phi, you have an inequality involving the integrals of the scalar curvature and the norm of the Ricci tensor. In particular, you can show that if you take the integral over the manifold of the square of the scalar curvature, then this is bounded above by 3 times the integral of the manifold of the square norm of the Ricci tensor. And moreover, equality in this inequality here holds if and if the intrinsic torsion from tau satisfies this equation here. So its differential is equal to the square norm of tau over 6 times phi plus 1 over 6, the Hodge dual of tau watch tau. And these are the so-called extremely Ricci pinched closed G2 structures. And if there will be time, I will say something about these structures in the next lecture. But for the moment, just compare this equation here for d tau, which means this condition of being extremely rich pinched, and compare it with the Einstein condition, which is this one. They are in some sense similar. You have similar summands appearing with different coefficients. And in fact, both these conditions here are instances of a more general condition that you can impose on tau that defines the so-called class of quadratic closed G2 structures, which was, for instance, deeply investigated recently by Ball. And if you have a look, so more generally, you can talk about quadratic closed G2 structures. And if you have a look on the archive, you will find a paper by Ball written in 2020, where he studies in depth this condition here, gives many examples of extremely rich pinched closed G2 structures, and so on. So if you're interested in this aspect, you may refer to that paper. Okay, so this is what I wanted to tell you about curvature properties of closed G2 structures. And this is what we know. There are also some extra properties proved by Clayton and Ivanov. And if you're interested in reading them, you can refer to their paper. So now we can move on and focus on the second part of this lecture that deals with symmetries of closed G2 structures. And in particular, in the construction of examples using symmetry techniques. So which is the idea here? So the general idea is that if you would like to obtain an example of 7-dimensional manifold, let's say compact or not, with an explicit closed G2 structure, then you have to consider a 7-manifold admitting G2 structures so with the right topology, as we saw in the second lecture, so it has to be orientable and spinnable. And you have to look for a 3-form phi such that, first of all, it has to be a section of the space of non-degenerate 3-forms. And then it has to satisfy this equation here, that on a given manifold, this is equivalent locally to a system of PDEs. And so in general, this problem is highly non-trivial to solve, and it might be difficult to find examples. Think, for instance, of all those examples that we mentioned last time where there exist torsion-free G2 structures. They required lots of effort to construct these compact examples admitting a closed G2 structure with suitably small torsion. And you have to use various types of analytic techniques to obtain these examples. So in general, you may impose some symmetries on the problem in order to simplify this equation you have here. So the idea is that symmetries may simplify the type of problem. For instance, you may ask your manifold, with the G2 structure to be homogeneous. This means that there exists a Lie group that acts transitively on N, preserving the tree from phi. In such a case, you have a presentation of your manifold as the quotient of G by some subgroup K, which will be the isotropy of this G action at some fixed point of the manifold, let's say X. And if K satisfies suitable properties, if for instance it is compact, so that you can consider a reductive decomposition of the Lie algebra of the Lie group G, let's say for instance as the sum of K plus a complement N, which is invariant under the adjoint action of K, then you can identify N with the tangent space to the manifold at the point X you have fixed. And you can translate every condition in conditions involving ad K invariant forms on this vector space. And in particular, the condition of phi to be closed will be equivalent to a system of algebraic equation. For a threefold defined on this vector space N, which is ad K invariant. Another possibility that has been widely considered in the literature is the case where this manifold is of homogeneity 1. This means that there exists a Lie group acting on N and preserving phi, and the principal orbits of this action, so the orbits whose codimension is the smallest possible, are hypersurfaces of the manifold N. And in such a case, it is a bit more involved to describe all the structure of the manifold, but let me just say that in such a case, the equation you would like to solve becomes equivalent to a system of ODEs for certain functions that you use to define the generic invariant 3-4. And so in particular, in both cases, you can see you have simplified in principle your problem, starting from a PDE problem, in one case to a problem of solving some algebraic equations, and in another case, you have reduced it to a problem of solving a system of ODEs on the manifold. That, of course, both problems might be highly non-trivial also in this setting, but in principle, they look simpler than the first case, the general case. And in fact, the first known example of compact 7-dimensional manifold admitting closed G2 structures that was obtained in the literature was given by Marisa Fernandez, and she obtained it on the compact quotient of a simply connected nilpotent Lie group endowed with a left invariant closed G2 structure. So you start with a homogeneous space, which is non-compact, and then you quotient it by a suitable subgroup that gives you a compact quotient. And since I will need this also tomorrow, let me just recall, and also because it is useful to see how the construction works, let me recall this example. So the first known example in the literature of compact 7-manifold admitting closed G2 structures and actually no torsion-free G2 structures was obtained by Marisa Fernandez in 1987. And the example can be described as follows. This is not the description that Fernandez gave, but it is equivalent. So it goes as follows. You consider the matrix group. Let's call it G, given by 5 times 5 upper triangular matrices of this form. You have 1, 0, x2, x4, x6, and you have 0, 1, x3, x5, x7, then you have 0, 0, 1, 0, x1, and then 0, 0, 0, 1, 0, and finally 0, 0, 0, 0, 1, such that the xi's belong to R. So this is a subgroup of the group GL5R, and G is equivalent, is isomorphic to the product of the generalized Heisenberg-Lie group of dimension 5 cross R2. And this was actually the description that Fernandez gave. So she focused directly on this group here, and then she took the product. But this description is equivalent. So this is the generalized Heisenberg-Lie group. And in particular, the coordinates we are using here with respect to this isomorphism here detect the components of the Heisenberg group for indices 1, 2, 3, 6, and 7, while this abelian factor here is determined by the coordinates x4 and x5. Now, once you have a matrix group of this type, you can consider its Maurer-Cartan form to compute a basis of left invariant one forms on this Lie group. And so in particular, if you take a generic element, let's call it G, and do not confuse it with the metric induced by a closed structure, you compute the Maurer-Cartan form. So G to the -1 dg, you can do this as an exercise and obtain a basis of left invariant on forms on G. And in particular, what you obtain are the following forms. Let me call them with EI with upper index. So these are equal to the xi for I going from 1 to 5. E6 is equal to dx6 minus x2 dx1, and E7 is equal to dx7 minus x3 dx1. And now you can compute the exterior differentials of these forms here and see that the forms EI for I going from 1 to 5 are or closed, while DE6 is equal to E12. So again, I'm using the shortening for the wedge product of covectors here. And the exterior differential of E7 is equal to E13. So in compact notation, you can say that this gives you the Lie algebra denoted as follows. You have 5 times 0, recalling that you have 5 left invariant 1 covectors that are closed, going with the indices from 1 to 5. Then you have E12, which is the differential of E6, and you have E13, which is the differential of E7. So this is a common notation that you can find in the literature to denote the isomorphism class of a Lie algebra. So the Lie algebra of this group belongs to this isomorphism class, and moreover, this is two-step nilpotent. As in fact, let's call this the algebra Gothic G. If you compute, and as you can see from this description here, the bracket of G with itself, you will see that it is contained in the center of G. And now, using this frame of left invariant 1 forms, you can construct a left invariant reform that defines a closed D2 structure on the manifold that is not co-closed. And in this case, the choice of the coordinates here was done in such a way that the tree form we want is precisely the tree form in standard form. So we have E123 plus E145 plus E167 plus E246 minus E257 minus E347 minus E356. And this is a left invariant 3 form on G on the group. So it is invariant by left translations of the group. And this defines a closed G2 structure that is not co-closed. So it is just a computation showing that its Hodge dual is not closed. Now, what happens is that there exists a co-compact discrete subgroup of this group G, which is given, let's call it gamma, it is given by considering the intersection of invertible 5 times 5 matrices with entries in Z with G. So this is a co-compact discrete subgroup of G. And so you can consider, you can let it act on the left and consider the quotient of G with it. Let's call it N for brevity. And this is a compact 7-dimensional nil manifold. Since G is a nilpotent group. And of course, since this tree form here is left invariant with respect to the action of G, and we are considering the left action of this co-compact discrete subgroup, we have that the tree form phi, which is left invariant, descends to the quotient. So it defines a closed G2 structure on N. So N phi is a compact 7 manifold with a closed and not co-closed G2 structure. And of course, this does not mean that this tree form here is the only closed G2 structure you have. There might exist also others. This is not a classification of the possible left invariant G2 structures existing on these closed G2 structures existing on this Lie group, but this gives you an example. So in general, there might exist others. So this was the first example known in the literature. And let me make some remarks on this. So first of all, we have that NT is a compact, locally homogeneous example. In fact, we took the quotient G over gamma with gamma acting on the left. So this is homogeneous with respect to the right action of G on this space, but the right action won't preserve the tree form defined by phi on the compact quotient. This tree form on this compact quotient is preserved by the locally defined left translations of G on the quotient G over gamma. So this is locally homogeneous, but it is not globally homogeneous. So in other words, the closed G2 structure you have on this compact quotient is not preserved by left translations globally. Moreover, from a theorem by Palais and Stewart, which goes back in 1960, we know that N is the total space of a T4 bundle over the three torus. And this is because the Lie group G is two-step nilpotent. So in particular, we have a fibration of this form, T4 going to N, going to T3, and this four-dimensional fiber is related to the center of the Lie algebra G, which in such a case is spanned by the left invariant vector fields E4, E5, E6, and E7 that are dual to the left invariant one forms we consider to define the left invariant closed G2 structure. And finally, N does not admit torsion-free G2 structures for topological reasons. And this is because, as Fernandez computed, the first Betti number of N is equal to 5. And then you can argue by saying that if there exists a torsion-free G2 structure, then it has to be Ricci flat. And then the harmonic representatives of the space of the first cohomology group must be 5 and linearly independent. And these would give 5 linearly independent parallel one forms on the manifold. But you know from the holonomy principle that any parallel object has to be preserved by the action of the holonomy group. And you do not have any connected subgroup of G2 preserving 5 one forms. The only possibility is that actually the holonomy is trivial and you have 7 linearly independent parallel one forms that are preserved, but then this would imply that the first Betti number of the manifold has to be 7, which is not the case. So from topological reasons, this example cannot admit torsion-free G2 structures. Okay, there is a related problem to this type of examples that consists in the classification of isomorphism classes of 7-dimensional Lie algebras admitting G2 structures. Because as you can see here, you have this presentation of your group as a matrix group, for instance, but you can work at the Lie algebra level once you know a basis of left invariant one forms. And so you can consider the structural equations of the Lie algebra and look for for three forms on the Lie algebra that define a G2 structure, so satisfy the topping condition, and so for which that symmetric to tensor B we consider in the last lecture as both determinant different from zero and is definite, either positive or negative, and also a tree form that is closed. So you need both these conditions to obtain a closed structure on a given Lie algebra. And so you can work at the Lie algebra level and then try to classify which Lie algebras admit closed G2 structures, of course in suitable classes. And in particular, if one is interested in compact examples, so let's say is interested in obtaining compact examples on compact quotients of this form, as in Fernandez's example, then one has to focus on unimodular Lie algebras. Which means that the trace of the adjoint of X is 0 for each vector X in the Lie algebra. And this is because Milnor proved that this is a necessary condition on a Lie algebra for the existence of lattices on the corresponding simply connected Lie group. And what we know so far about this classification problem, well, we have a classification by Conti and Fernandez of, in the case where G is nilpotent. So for nilpotent Lie algebras, we know which isomorphism classes of nilpotent Lie algebras admit closed G2 structures. And this result was obtained using a case-by-case analysis going through the 149 possible isomorphism classes of nilpotent Lie algebras in dimension 7. And what they obtained is that there are 12 cases out of 149, including the abelian Lie algebra. And this was obtained in 2011. Then recently, together with Anna Fino, in 2019, we obtained a classification in the case where G is non-solvable and unimodular. And also in this case, you can obtain a structure result for the Lie algebra and describe up to isomorphisms, which are all the possible 7-dimensional non-solvable unimodular Lie algebras admitting closed G2 structures. And in the solvable case, so when the Lie algebra is not only nilpotent but also solvable, we do not have any classification result for 7-dimensional solvable Lie algebras up to isomorphism. And so, for instance, if one is interested in classifying certain classes of solvable Lie algebras admitting closed G2 structures, then one has to impose some extra assumptions on the Lie algebra. And for instance, we did this again with Anna Fino and Francesca Salvatore. And this was done in 2021. What we did is to obtain a classification in the case of solvable Lie algebras that are unimodular and have non-trivial center. So these are the known classification results for Lie algebras admitting closed G2 structures. There are further classifications for the algebras admitting closed G2 structures satisfying some extra properties. And if I will have time, I will mention them tomorrow. And so let me just remark regarding this last classification that, of course, here we made this extra assumption on the solvable Lie algebra. And so in particular, even there are known examples of solvable Lie algebras with trivial center admitting closed G2 structures, we do not have any classification in that case. So we could say that in that case, the problem is still open. So let's say classifying solvable Lie algebras admitting closed G2 structures in greater generality. Okay, so this is what's going on for Lie algebras, and so for associated with them, simply connected Lie groups admitting left invariant closed G2 structures, which is a particular instance of non-compact homogeneous manifold admitting invariant closed G2 structures. So in general, what one might ask is, what can we say about compact homogeneous examples? Since, as I remarked before, even if there exists a quotient of the simply connected Lie group induced by the Lie algebra by a compact discrete subgroup, then what we will get is a compact example that is only locally homogeneous but not globally homogeneous. So it is not homogeneous with respect to the left translations of the Lie group. So in this setting, there is a classification of compact homogeneous spaces admitting closed G2 structures that are invariant, and it was obtained by Reidegeld in 2010, and he obtained a classification of compact homogeneous 7 manifolds admitting invariant G2 structures. And he also proved that any possible example that occurs admit an invariant co-closed G2 structure. So for the co-closed case in the homogeneous setting, we know that every compact homogeneous 7 manifold admitting invariant G2 structures also admit a co-closed G2 structure that is invariant. And most of these examples are actually nearly parallel G2 structures, which is one other possible class of G2 structures arising in Fernandez and Gray classification, which is given by G2 structures inducing in particular an Einstein metric. So so there exist invariant co-closed G2 structures in every case on every possible manifold, and most of them are actually nearly parallel. Which means that d phi is equal to tau 0 star phi, and where tau 0 is the unique non-vanishing intrinsic torsion fold, which has from this equation necessarily to be constant, and so this implies in particular that phi is co-closed. So in such a case, tau 0 is a constant, and the induced metric is Einstein. And let me remark that the invariant compact homogeneous spaces admitting invariant nearly parallel G2 structures were studied by Friedrich, Katt, Moroiano, and Zemmelmann in 1997. And so if you're interested in this class, that is also another remarkable class of G2 structures, and you're interested in homogeneous compact homogeneous examples, you may refer to the paper. So in any case, we have this classification, but we do not know whether there exists invariant closed G2 structures on any of these spaces. And the idea to study this problem might be focusing more generally on the automorphism group of M compact submanifold with phi closed G2 structure. In order to understand whether there might exist compact homogeneous examples admitting invariant closed G2 structures, and more generally, which type of compact examples of manifolds admitting closed G2 structures that have a large symmetry group may occur. And this what I did together with Fabio Podestà, and I'm going to talk about this result in this last part of the lecture. So which is the idea? Is focusing on the automorphism group of M. And so in general, this automorphism group, so from now on, I will assume that M is compact. And for the moment, let's give the definition, the generic definition, which holds for every G2 structure phi. The automorphism group is defined as the group of diffeomorphisms of the manifold that preserve the tree-form phi defining the G2 structure by pullback. And clearly, since the tree-form phi, the G2 structure phi, induces a Riemannian metric, any diffeomorphism preserving the tree form will also preserve the Riemannian metric it induces. And so in particular, it will be an isometry of the Riemannian metric G phi. And so in particular, the automorphism group will be a subgroup of the isometry group of the Riemannian metric, which is the group of diffeomorphisms of the manifold preserving the tree form by pullback. The Riemannian metric G phi by pullback. Now we know in general that if M is a compact manifold and G is any Riemannian metric on it, then the isometry group of the Riemannian manifold has to be a compactly group by a theorem of Myers and Stanford. So we know that this is a compact the group by a general result by Myers standard. And if you're interested in it, it is the paper published in 1939. So this is a compactly group, and the automorphism group of the manifold with the G2 structure phi is a closed subgroup. And so in particular, the automorphism group of a compact manifold with a closed G2 structure is a closed and hence compact Lie subgroup of the isometry group of the compact manifold with the Riemannian metric G phi. So it is a Lie group, and you can consider its Lie algebra. And its Lie algebra, since the manifold is compact, will be given by the set of vector fields on the manifold that preserve the tree form when you take the Lie derivative. So the set of vector fields for which the Lie derivative of the tree form with respect to the vector field is equal to 0. And this is contained, of course, in the Lie algebra of the isometry group of M, which is the Lie algebra of killing vector fields for the metric. So in particular, every vector field X, which is an infinitesimal automorphism of the G2 structure, so which belongs to the algebra of the automorphism group, is a Killing vector field for the Riemannian metric G phi. And now, using the properties of the three-form phi, you can deduce properties of the Lie algebra of the automorphism group. So the idea in general is that information on the Lie algebra of the automorphism group can be deduced from properties of the G2 structure phi. And let me just remark this, since I mentioned this fact in the last lecture. For instance, if phi is torsion-free, then what we know is that the Lie algebra of the automorphism group has to be abelian. So all brackets of its vector fields are 0. And this is because a torsion-free G2 structure, as we saw in the last lecture, induces a Ricci flat metric. And then this implies that every Killing vector field has to be parallel with respect to the Levi-Civita connection induced by the metric G. And this follows from Bochner formula on the compact manifold. So in particular, again, we have some parallel vector fields, and so they have to be preserved pointwise by the action of the Delaunay group, by the Delaunay principle. And so in particular, the dimension of the Lie algebra of automorphisms is equal to 0 if the Delaunay of the metric is precisely the G2, since pointwise, in such a case, G2 only preserves the 0 vector in the 7-dimensional representation we have. So it follows from the Delaunay principle and this fact that in this case, the automorphism group has trivial Lie algebra. And so in particular, since the manifold is compact, the identity component of the automorphism group and the automorphism group itself has to be finite. So you do not have continuous symmetries. And you have other observations that you can make here is that the dimension of the automorphism, the algebra is 1 if the Delaunay group is SU3, since in such a case you have a one-dimensional subspace of the 7-dimensional representation that is preserved by SU3. The dimension is 3 if the Delaunay is SU2, and the dimension is 7 if the Delaunay group is 3. Other possibilities known in the literature are, for instance, the properties of the automorphism group when the G2 structure is nearly parallel. And you may refer to the paper by Friedrich Kapp, Moroyan, and Zemmelmann that I mentioned before, if you're interested in them. And in particular, what they proved is that if you have a compact 7-dimensional manifold that endowed with a nearly parallel G2 structure, and the manifold is not isometric to the 7th sphere, then the dimension of the automorphism group is bounded above by 13. And if the dimension is greater than or equal to 10, then the space has to be homogeneous. This is the result, and I invite you to refer to their paper if you're interested in the proof and in seeing which is the list of possible compact homogeneous spaces admitting nearly parallel G2 structures, which are invariant, and by the way, will induce an invariant Einstein metric on the space. So this is more or less the general picture. And when we have a closed G2 structure, so the case on which we are interested today, then what we can prove is the following. We have this theorem that I proved in collaboration with Fabio Podestà, and this was in 2018. So if you have a compact 7 manifold, with a closed G2 structure, then what you can show, first of all, is that also in this case, the Lie algebra of its automorphism group is abelian, as in the case of torsion-free G2 structures. But here, this fact immediately follows from the fact that all Killing fields are parallel and the fact that the Levi-Civita connection is torsion-free. So the Lie algebra of the automorphism group is abelian with the dimension bounded above by 7. And moreover, dimension bounded above by 6 if phi is closed but not co-closed. So if phi is not torsion-free. Moreover, the dimension of the algebra of the automorphism group is also bounded above by the second vector of the manifold. If furthermore the dimension is greater than or equal to 5, then the identity component of the automorphism group acts freely on the compact manifold, preserving the triform phi. So this means that the isotropy at each point of the manifold is trivial. And finally, if the dimension of the Lie algebra of the automorphism group, and so of the automorphism group, is precisely 6, then the manifold has to be diffeomorphic to the 7 torus. And as a consequence of this fact, you obtain that if you consider an phi compact 7 manifold with phi closed G2 structure and not torsion-free. So if you're interested in compact 7 manifolds with a closed G2 structure that is whose, let's say, intrinsic torsion form tau is non-zero, then the dimension, the automorphism group as abelian Lie algebra with dimension bounded above by a minimum between the 6 and the second Betti number of the manifold. This implies that there are no compact homogeneous examples because of this bound here given by 6, and moreover that M phi can be of homogeneity 1 only when M is diffeomorphic to the 7 torus acted on by the 6 torus. And examples of this type occur. So the bound given by 6 here is actually sharp. So let me give some ideas on the proof in this last part of the lecture. So we have a closed G2 structure and a compact manifold. Let us consider a vector field X, which is an infinitesimal automorphism for the closed G2 structure. Then, by definition, the derivative of phi with respect to X is 0. But then, using Cartan formula, what you have is that this is equal to the differential of the contraction of phi with X plus X, the contraction of d phi with X, but phi is closed, so this is 0. And so here you get the differential of the contraction of phi with X, which is equal to 0. And so in particular, this contraction has to be closed, is a closed to 4. But if you remember, a two-form of this type is not any two-form. This belongs to the space of two forms that is modeled pointwise on the 7-dimensional irreducible submodule of the space of two forms. And so in particular, what you have is that this contraction pointwise belongs to lambda to 7. And so this means that if you take these two forms and you take the wedge product with phi, then as we saw in the second lecture, in the first lecture, this is equal to twice the Hodge dual of the contraction of phi with x. And as you can see now, on the left-hand side, you have a closed form. And so this implies that the differential of the Hodge dual of the contraction of phi with x is 0, and so that x contraction with phi is co-closed. So this is both closed and co-closed, and this means that it is harmonic. And so we get an injective map going from the Lie algebra of the automorphism group to the space of harmonic two forms, sending an infinitesimal automorphism x to the contraction of x with phi. And recall that this map is injective because phi is non-degenerate, and as we remarked last time, this implies that this map is injective. And so in particular, this implies that the dimension of the algebra of the automorphism group is bounded by the second Betti number of the manifold, which is the dimension of the space of harmonic two forms on the compact manifold. Moreover, how to show that the automorphism in the algebra is abelian? If you pick two vector fields belonging to the automorphism in the algebra, then they are in particular, as we said, Killing vector fields for the metric G induced by the three-form phi. This implies that if you take the Lie derivative of the contraction of phi with x with respect to y, then this will be 0. And this is because the contraction of phi with x is a harmonic two form, and Killing fields preserve harmonic forms on compact manifolds. And so from this, by applying the interplay between the Lie derivative and the contraction, at the end of the day, you will get that this is equal to the contraction of the bracket of y and x with phi plus the contraction of the Lie derivative of phi with respect to y with x. But again, this is 0 because by hypothesis, y is an infinitesimal automorphism of the G2 structure. And so as you can see, you get this contraction that has to be 0, but since this contraction is injective, this implies that the bracket of any pair of vectors in the automorphism in the algebra has to be 0. And so that the automorphism in the algebra is actually abelian. So now what you have, let me just say this, and then if you are interested in the complete proof, you may refer to the paper. What you have now is that the identity component of the Lie algebra, of the automorphism group is a torus, since it is a compact abelian Lie group, and it acts effectively on the manifold. And this implies the principal isotropy. So the isotropy of this action that has the smallest possible, the isotropy subgroup of this action that has the smallest possible dimension is trivial. And since the orbits are injectively immersed in the manifold, this implies that the dimension of the automorphism, the algebra and so of the automorphism group is at most 7, which is the dimension of the manifold. And if the dimension is precisely 7, then you can identify, let's say, M can be identified with the 7th torus endowed with the flat G2 structure. Which means torsion-free and inducing a Riemannian metric which is flat. And this is not possible if we assume that phi is closed but not co-closed. And so this implies that in the case where phi is closed but not co-closed, the bound on the dimension is given by 6 instead of 7. And so for further details, refer to, if you're interested in reading the further details on this proof, you may refer to the paper. Okay, so in conclusion, let me remark some other facts that we know about the setting. So about the setting of G2 structures with large symmetry group on compact manifolds, and also in the non-compact case now. So together again with Fabio Podestà, we also obtained a classification of non-compact G-homogeneous spaces admitting invariant closed G2 structures for G are reductive Lie group, which means that it's the algebra splits as the sum of a semi-simple part and the center, so an abelian factor. And in such a case, you can show that if you assume the action to be irreducible, so if you assume that no normal subgroup of G acts transitively on the manifold preserving the closed G2 structure, then what you can show is that the dimension of the center is necessarily 1, and the possibilities for the Lie algebra of the semi-simple part of G are either SU21 or SO41. These are the only possibilities you have for in the non-compact homogeneous setting when the group is reductive. And in particular, it follows from the previous result in the compact case and from this result here that if you have any 7-dimensional manifold with a closed G2 structure that is not torsion-free, then a group acting transitively on it, preserving the G2 fold, cannot be semi-simple. Moreover, so this was obtained in 2019, if you're interested in the paper that can be found on the archive. Moreover, we have complete, in the cohomogeneity 1 case, we have some complete cohomogeneity 1 examples that were obtained with, of course, phi that is closed and not torsion-free, that were obtained by Clayton and Swan in 2002. And they are cohomogeneity 1 examples with respect to the action of a simple group. And in particular, with respect to the action of the simple groups SU3. So we have some examples of this form and some examples that are of homogeneity 1 with respect to the action of the group sp2. And what they observed is that these examples, that are of course non-compact, only occur on manifolds that admit invariant G2 holonomy matrix. And so on the examples that were first found by Bryant and Salamons on the space of anti-self dual 2 forms over the full sphere and the space of anti-self dual 2 forms over the complex projective plane. We have more known examples on the groups, of course, non-compact examples. We need more examples on simply connected. The groups are known. And maybe I will say something about this in the next lecture, because in these many examples we have of simply connected groups with a left invariant closed G2 structure, the G2 structure the closed G2 structure satisfies some extra properties. For instance, it is a soliton for the Laplacian flow. It is an extremely rich pinched closed G2 structure according to the definition stated earlier. And so there are various, as you may imagine, this setting of Lie groups provides a fruitful setting. We're looking for examples of closed G2 structures that are not torsion-free. And finally, let me remark that recently, in the compact non-homogeneous case and neither homogeneity 1 case, there was an example obtained by Fernandez, Fino, Kovalev, and Munoz that goes back to 2019, who obtained a compact example admitting closed G2 structures and no torsion-free G2 structures whose first Betti number is equal to 1. And this is the smallest possible Betti number that a compact manifold admitting closed G2 structures is known to have. So in particular, for instance, we do not know whether there exists a compact 7-dimensional manifold admitting closed G2 structures that is simply connected. So this is an open problem so far. And this example here was obtained following the idea by Joyce of considering an orbifold and then resolving its singularities. And so again, if you're interested in this example, you may refer to the paper for the details. And okay, I think this is all I wanted to say for today. And so thank you very much for your attention.
All right. Thank you very much. Any questions? All right. Thank you very much for the nice talk.